Everyone has probably heard about the Titanic disaster, but have you ever wondered if you would have survived it? I have created an AI model to predict survivability based on passenger information, and today, I will show you how to train models like this and explore some interesting results. For training the model, I used Keras and TensorFlow in Python, which are popular solutions. The dataset is publicly available, for example, on kaglu.com, but it's not the only source. You can find the dataset link in the description. The dataset contains information about passengers, including their names, ages, ticket classes, cabins, ports of embarkation, number of family members on board, etc., covering about 900 individuals. There is also a test set with an additional 400 entries, but without the survived column, as the dataset was originally used for a competition where predictions for this file were evaluated. Since I couldn't use it for training, I left it out. I split the dataset with 900 rows into 3 separate files, one for training, one for validation, and one for testing. During training, the model's accuracy is evaluated using the validation dataset, which helps tune the model and monitor overfitting. However, since the validation set may not fully represent real-world data, it is not a perfect measure of performance. That's why the test dataset is important. It is completely separate and has not been used at any stage of training. I also created a directory for storing trained models. Splitting data into multiple files is not required. You can load everything dynamically and use a specific function to randomly split the data, but I chose to do it manually. Before training the model, the data needs to be prepared. Since I had 3 different dataset files, I created a function for data preparation to avoid duplicating code. In this function, some columns are dropped. I believe that passenger names, IDs, and ticket numbers are not related to survivability, so these columns are unnecessary. The in-place parameter ensures that the operation is performed directly on the variable, otherwise, an assignment would be required. In the next step, rows with missing age values are dropped. This is one possible way to handle missing data. Another approach is called imputation, which involves filling in missing values, usually with averages. For missing age values, I chose to drop the column, while for missing embarkation data, I filled in the most common value. Finally, a label encoder is used to convert text values into numbers. Since neural networks require numerical inputs, text data must be encoded first. In this dataset, columns like sex and embarked contain text values that need to be transformed. In the final step, the survived column is dropped from the input data because it should be the output variable and is assigned to the y variable. This function is applied to all dataset types. Then, the data is standardized using a standard scalar, and a directory is created for the new model, where the scalar and encoder files are saved. Next comes the most important part: training the model. The model consists of an input layer and 3 dense layers. In simple terms, a dense layer in a neural network means that each neuron in that layer is connected to every neuron in the previous layer. This type of layer is sometimes called a fully connected layer. Each layer has a specified number of neurons and activation functions. To achieve better results, experimenting with these parameters may be necessary. There are no universally best values that work for every dataset. I used the atom optimizer, which updates the model's weights based on gradients. The loss function used is binary cross-entropy, which measures how well the model's predictions match the actual target values. This loss function is commonly used for binary classification tasks, making it a good choice for this example. The evaluation metric is accuracy, which is used to assess the model's performance during training and testing. Accuracy is calculated as the number of correct predictions divided by the total number of predictions, or samples. For this dataset, this configuration works fine, but it is probably not the best one. The results are similar across different setups, and I observed that the pattern is learned very quickly. To save the best model, I added a checkpoint. This part of the code is executed at the end of each training epoch. If the accuracy on the validation dataset improves, the model is saved. Additionally, after each epoch, the results on the training dataset are printed. I set the training to run for 50 epochs, but as I observed, good results are achieved much earlier. The final accuracy on the test dataset is over 80%, which indicates that the model has learned a pattern. A result close to 50% would suggest that the model is making random guesses. A result above 80% indicates that the model is not just relying on luck, but has identified meaningful patterns in the data. But what happens if we remove certain columns used in training? I tested this by dropping different columns that likely influenced survival during the disaster. The results were worse. For example, without the sex column, accuracy dropped to just 72%. Removing more columns made the results even worse, suggesting that these factors likely played a significant role in determining a person's chances of survival. The model learned a pattern specific to this disaster. Since the achieved results are based on unseen data, it increases the likelihood that the pattern is real. Then, I created a second file where the trained model is used to make predictions based on input provided from the console. Loading the same scaler and encoder as in the training process is important to ensure that the input data is encoded and scaled in the same way. The prediction output is always a value between 0 and 1 in this case, but it will usually not be exactly 0 or 1. The result indicates class membership. The closer the value is to 0, the higher the chance it belongs to class 0. The closer it is to 1, the higher the chance it belongs to class 1. Typically, a value above 0.5 is classified as class 1, while a value below 0.5 is classified as class 0. In my example, class 1 is survived and 0 not survived. Result is printed in the console. In this way, you can pass information about any person to check what their chances would be if they were there. Of course, this should be taken with a grain of salt. It is based on data, but there have been exceptions, which is likely the main reason why the model cannot achieve near 100% accuracy on unseen data. If you want to experiment with this project, you can find the code on the GitHub link in the description. Finally, take a look at a few final examples.